Good morning, everybody, and welcome to this application from Chapter 36, basically. So we covered, in terms of the content, we covered everything there is to cover in terms of the big concepts that we started with. Let me just give you a refresher. We started a long time ago with fluid dynamics, actually, Chapter 12. That was on February 16th. When the college started. Actually, we first met on February 17th. Anyway, so we started chapter 12 doing the hydrodynamics, basically fluid dynamics. We talked about the hydrostatics first and the conditions of liquids, basically in terms of their equilibrium or static conditions, namely that the fluid is not moving. Then we went to fluids that are in motion. And we defined two kinds of behavior. There was the laminar flow, and there is also the turbulent flow. We couldn't deal really, and we cannot really deal at this level with turbulent flow, the laminar flow. And then from there, we derived basically Bernoulli's equation, which is really a conservation of energy equation. It tells you basically the condition under which the kinetic energy of or a kinetic energy per unit volume, really, because it involves the density of the fluid times the velocity squared. And that is actually in relationship also with the gravitational potential energy per unit volume also, because that also involves rho times g times the height. And that is equal to the difference in pressure from both sides, basically what causes the flow of the fluid to go from one location to the other. So that was really chapter 12 from the book. Then we jumped into wave mechanics. Yes, we studied first of all oscillations. And we found that if I take a mass spring system, for example, it oscillates with a frequency that is the ratio of the spring constant over the inertia, but in this case, over the mass really, but in this case under the square root. So that was the velocity with which it moves. Yes, the angular velocity, I should say, square root of k over m, where k was a spring constant. And we took that idea, we studied it, we studied the conditions basically of oscillations and different kinds of other oscillations, mechanical systems and everything else, like the torsional spring and so on and so forth. Then we went to waves. Waves is similar to oscillations in the sense that they both have temporal behavior that is changing with time at irregular rates, namely the angular frequency, but then waves actually travel in space. So we did actually the one-dimensional wave on a string, and we generalized the idea on other things. It turns out the velocity of the wave was proportional to actually the square root of the tension in the string, in that case, divided by the linear mass of the spring, or the mass per unit length. And then we also took that idea and we generalized for sound, which is really a three-dimensional wave that travels in space. And we basically did not derive the expression for the velocity for it, but we took an analogy with the some sort of an elastic property, which turned out to be the bulk modulus of the medium, divided again by the density of the medium, which is in this case in the air, it's rho, just the density of air, which is 1.29 kilogram per cubic meter. Anyway, so that was really the idea, that it turns out that the velocity is actually temperature sensitive, and that's the idea with it. Then we introduced thermodynamics in full-fledged. Basically, we found three laws that govern it. The second law of thermodynamics was the law of the entropy. And basically that a system given on its own, its entropy will increase, or that's one way of putting it, or in this case, heat does not flow spontaneously on its own from a cold source to a hot source. That was the second law of thermodynamics that Mr. Carnot has formulated. Then we introduced actually before it the first law, which is really a statement that the total energy of the system is conserved, in a sense that heat and work can be exchanged during a thermodynamic process in such a way that that amounts to the total change of the energy of the system. Pumping heat and the temperature increases, or the internal energy increases, extract heat and the temperature of the fluid, whatever the medium, is going to go down, and namely the internal energy is going to be less because you removed heat from it. Also, having a system doing work against the environment requires some energy from somewhere. So it must come from its own inside. So that also amounts to decreasing the amount of energy in the system, or having the environment do work against the system, in this case, also amounts to adding more energy into the system coming from the environment around it. So that is the principle of a piston, really. So that is really the first law of thermodynamics. But before we talked about all of this, we really needed to introduce the temperature. So we needed the zeroth law of thermodynamics that basically says we had to have some sort of an intuitive notion of what thermal equilibrium is. So thermal equilibrium is when two objects have the same feel in terms of temperature. We say at that point that they have reached thermal equilibrium. So that was one notion. Then if I take a system A, we call the system A, and it was in thermal equilibrium with system B, and system B turned out to also be in thermal equilibrium with system C, then the zeroth law state that system A and system C are actually in thermal equilibrium. That allowed us to invent the thermometer and define what the temperature was. So we have a way of measuring temperatures at that time. So basically, that is the idea for thermodynamics. Turns out there are all kinds of properties we can calculate. The PV diagram is one of them. And on a PV diagram, we calculate the work, we can calculate the efficiency of the engine, if it's an engine, or the performance of a refrigerator or a heat pump, if in case it's a heat pump. So that was really the good chunk of the course we spent on that. Then we went and jumped several chapters that are covered in another class, actually Physics 4B, and to Physics 4, into optics. We started with the simple geometrical optics, in a sense that objects basically objects do. Light behaves like a particle in a sense, and we have two basic laws there. A law of reflection, that the angle of incidence is equal to the angle of reflection, and the law of refraction, in which case that the angle of reflection and the angle of refraction and the angle of incidence are related via the ratio of the indices of refraction of the two media. In other words, n1 sine theta 1 is equal to n2 sine theta 2, where 1 refers to one medium and 2 refers to the other. Okay, so that was the law of refraction and reflection. It allowed us actually to start thinking in terms of when light meets coming from an object, it's going to form an image of that object, depending on whether or not we're looking at a reflective device or a refractive device. With the reflective devices, we were able to introduce the flat mirror and find the image, how it forms on it. And it turns out it's going to be an exact replica, with the magnification being exactly 1, and the only thing that is not conserved in there is going to be the left and right. But other than that, the object was upright, the object was magnification was 1, and the image was actually virtual, not real. So that was the flat mirror, and then we have that was actually a reflective mirror, and then we have also all three mirrors that we introduced are reflective mirrors, by the way. Then you have the concave mirror and the convex mirror. Convex mirror always forms virtual images, and the magnification now depends on how far the object is from the focal, how far it is from the mirror in comparison to its focal length. Same thing with the concave mirror. Concave mirror can form virtual images. For the most part, it forms real images because of the fact that depending on how far the object is, if it is less than the focal distance, then in this case, the image is going to be virtual. Other than that, the image is going to be real. If the object happened to be just on the focal point, the image is far away, it's on the infinity. So that was basically the image formations using reflection. Then we have also refraction. Refraction can be in terms of the lenses. So lens is a medium with different index of refraction. You have light coming from one side, and it goes through that medium, slows down in a sense, and then goes to the other medium, and then the images also are formed. Again, a convex lens will form real images or virtual images depending on where the object is sitting. Okay, a real image in the case of a convex lens is going to be on the other side of the lens if the object is on this side. and the virtual image will be on the same side of the object. In that case, if the object happened to be less than the focal length from the lens itself, then in this case the image is going to be virtual, which is critical. That is actually how magnifying glasses work, because then you can put an object very close to the magnifier, to the lens, and the image will be moved away from you at the comfort zone for your viewing. Then we also have the convex lenses. Convex lenses form always, concave lenses form always virtual images, just like the convex mirrors do. So again, that was a big topic in there for image formations and resolution and things like that. Then we went into wave optics, I'm sorry, where we basically stated the fact that light is actually not particles, and all of those things can be explained in terms of Huygens principle. And Huygens principle basically states that Huygens Fresnel principle, sometimes there's also the Fresnel, because both of them worked on this stuff, that basically each point on the wavefront becomes a source of new wavelets, and that is the envelope of those wavelets form the new wavefront. And that allowed us to understand, among other things, a double slit experiment, in the sense that if I have a monochromatic beam of light going through a medium, through two slits, and the two slits have the separation distance between them, d, then in this case, the central point, which is the opposite to the middle point between them, is going to be a bright fringe. There is always no problem with it. But then there is a dark fringe that forms immediately, followed by another bright fringe where the path taken by the two slits, basically light emanating from the two slits, is a multiple integer of lambda. So there will be actually a bunch of them, not just one. Okay, how many there will be, it depends on sine theta. If sine theta starts to become bigger than 1, then of course you cannot have an angle where the images form. So we did not really do a lot of problems, and we're going to do today some problems with that. But the point being, in here, you can't have willy-nilly a given number of slits in here. There is a limit to how many you can have, and that depends on the ratio of lambda over d. Because again, sine theta is equal to m times lambda over d, so you require that the number m, which is how many bright fringes I'm going to find above let's say, for example, the central fringe. If m is negative, I'm going below, that's all. So if I'm looking at the above, then it's m times lambda over d must be less than 1. So that is a condition for me to find how many m's I'm going to have, because if I do this inequality, it gives me m must be less than or at most equal to d over lambda, but it's an integer. So that allows me to find how many bright fringes I can find above and bright fringes below, since it's going to be symmetrical, since there is an m number above and an m number below. So it's going to be an even number when I multiply that by 2. But don't forget the central fringe. That is m equals to 0. So it's going to be an odd number at the end of the day. Okay. So that is basically the double slit. The single slit is similar to the double slit in a sense. The analysis is slightly different. So you have only one opening, and you have light coming from the other side, but the opening is small. Now A is smaller than D, relatively speaking. Then in this case, I can assume each point on the single slit as being a source, again using Huygens principle, and make the following argument. It's hard, and it's very hard to find the bright fringes, but I can very easily find the dark fringes in this case, the dark spots where all the cancellations happen. Well, I can think of A, that this the distance, basically the opening of the single slit, how wide it is, that it's made up basically of the upper half and the bottom half. When the upper half and the bottom half meet with a half wavelength, then it's destructive interference. That gave us a condition on finding the dark, basically, points where they cancel out. So now, and the dark condition is just basically A over 2, because I divided A in half, times sine of theta must be equal to a half integer of lambda must be like the first one would be m time, the first one would be 1/2 of lambda, cancel the half on both sides, and it gives me conditions similar to the double slit. Instead of D, I have A, where A sine theta is m lambda. M cannot be 0, but anything in between them is good, because 0 corresponds to a bright fringe actually. And the center, as a matter of fact, it's twice as wide as any of the others. So that is basically the conclusion that we came up for the single slit. So this is in a nutshell your entire course. I summarized it in 15 minutes, the entire course from February 17th until today. Okay, everything that we learned in this class. So let me do a demo for you guys. First of all, let me switch cameras in here and do a demo for the diffraction grading, because it illustrates the last 2 points in here. So here is a diffraction grading. I have, is the mirror correct? It looks like it's backward. Hold on, I didn't need to turn it off. It says 500, looks like it's reflected. Looks like it's a mirror. So can I change the setting in here? Video settings, and hopefully don't do a mirror. Okay. It still shows. Can you read this number, guys? It looks like it's correct now. You can read it, can't you? This is 500 lines per millimeter. Yes, no? As opposed to this one. This is 1,000 actually. Yes, can you read it or not? I'm looking at the chat now, I want to know. Okay, very good. So this one is 1,000 lines. That means that there is 1,000 lines in here for every millimeter. So if I want to know how far apart they are, so basically what it is openings. So how far apart, every millimeter there is 1,000 lines. So each one of them between 1 and 1 is 1/1,000. Very, very small distance between the slits. Whereas in here it's twice as much, because I only have 500 lines per millimeter. So what I'm going to do now is I'm going to do an experiment. Now I have 2 laser beams. Let me see if I can read the numbers in here. I don't even have my magnifying glasses in here. But the red light is somehow about 600 and something, 640 nanometers. They usually give you the number on them. Yeah, assuming it's 640 nanometer, because I can see it well. Even with these glasses, I cannot see it well. Okay. So this is 600, and this is the green light. It should be around 300, maybe around. Oh, I can see it in here. It says 522 nanometers. This one is 592 nanometers. Let me see if this one now I can find it. It's 650 nanometers. Okay, this is 650. This is 522. Okay. So what I'm going to do is, first of all, I'm going to switch cameras. Okay, let me show you the setup. Let me first move this up a little. So what I have in here, I'm trying to have this one as a holder for my diffraction grading. So I'm going to start with 1,000. I'm going to put it in here so that it holds for me. Okay. Don't laugh at my lab, okay? Because I'm trying to get something done in here. We're not in the lab to have all kinds of nice equipment. So what I'm saying in here is that I want to keep this distance the same, okay? If you see the ruler in here, it has a 15 centimeter, and there is the 14 centimeter, the 13 centimeter, 12 centimeter, 11 centimeters, and so on and so forth. So this is basically your R distance in the formulas we've been using. So assume that this is the screen. This is your slits where they are located. It's coming from here, so not this one. This one I still didn't put it this. I put the 1000. So in other words, the distance d is so small between them. So because the expression says d sine theta is equal to, the first one is going to be m equals to 1, so it's equal to lambda. So I expect sine theta to be lambda over d. If d doubles, and it's going to double from this one. Right now it's small. It's 1 over 1000, and then when I place this one, it's going to be 2 over 1000 or 1 over 500. So in this case, d has doubled in size. Since d doubled in size, when I go to this one, then I expect the sine theta to be less. So let me demonstrate this one in here. So I'm going to use the same light. Okay, I'm going to use the green because it's super bright. I don't know if you can see it or not. So right now, the central fringe is at 15 centimeters. And the first bright one, I'm looking to one of them, okay? I'm looking to this side in here. So it's at 12, basically, centimeters, okay? So I need to put my hand in the same location, okay? So that's when I change these things and I put the new one, nothing changes so that the source of the light beam stays in the same location. I'm gonna use the same thing in here. So, and here is the first one. The first one, remember, was at 12, okay? Now it moved to about 13.5 centimeters, closer. In other words, sine, oh, I'm sorry, probably it's too bright. Okay, let me use the red light, okay? Red light is less intense. I didn't see that it was going this way. So again, let's do the red light. The red light right now, it's 13.5 centimeters, okay? Or did I move it? So the central fringe is at 15, and the first one is at 12.5. Let's call it 12.5, okay? Again, I'm gonna change, so this is twice as much. So now when I make d smaller, remember d is in the denominator, so theta should be bigger now. I need to change it. Sometimes it doesn't do. Okay, it's definitely bigger. You can clearly see it's about 11. This is what it is now. It's way back in here, okay? On the other side. It's way back on this side, okay? So let's keep it at 15 centimeters, the center bright fringe. So this is basically what happened in here. So this is the effect of D. Let's keep this number in here of D basically is equal to 1 over 1000. I'm going to change the wavelengths now because remember the numerator has lambda in it too. So I have the, right now I have the 650 nanometer. The 650 nanometer is in the numerator divided by D. If I do that, then there is an angle. But if I change it to the green one, which is less, lambda is less, the angle should be less. Because again, sine theta is lambda over D. Okay, so let's do that. Right now, the central fringe is at 15 centimeters, and the first one is at 11. So I'm always looking at this one, okay? I'm looking at this angle in here, okay? So the first one is at 15 centimeters, the second one is at 11 centimeters. Now I'm going to change source, and hopefully it's not too bright for you guys to see it. So the first one is at 11, and the second, the first one is at 15. The second one has moved all the way to 12. I don't know if you can see it or not, because it was way on the other side, okay? Now it has moved closer to about 12. So that's the whole point of this exercise. Let me first of all switch back to the regular camera. As D changed and doubled in size, sine theta became less, so theta became less, okay? As lambda also changed in size from a big value, from the red value to the green value, also it shrunk, basically going from 650 nanometers down to 522 nanometers. So in this case also, sine theta became smaller. So that is the formula that we're working with. This is a diffraction grading, and it's a very, very good actually device to separate lights. So if you have a white light coming through it, imagine that there is the red light and the green light coming together. When they go through the diffraction grading, they will be split, and you can clearly see one angle for one and the other angle for the second. That is the usefulness of the diffraction grating. It can be used as in spectroscopic devices, basically to do spectroscopic analysis. It's used actually in on big, large telescopes that collect light from the stars, and as light goes through it, it's split based on the frequencies that you see there, based on the light they collect from there. You can tell. You're going to make a spectrum, basically. You're going to make a whole, basically, in this case, is going to be a spectrum of the light source that sent that light. Then you can tell the properties of the material that sent it based on that. There is a big branch of physics, and actually there is a boundary in there with chemistry about the spectroscopy, and it's all based on this principle, because light is split now, just like a rainbow. But now you have a control over it of how much you want them to be going one way or the other. So it's really very powerful stuff in here. Okay, so let's get into the applications of these things. Let me share with you the screen. We are meeting on Monday, okay? We have a class on Monday where we do more applications. And then after that, it's up to you guys if you want to meet or do more stuff and things like that, okay? So, let me start from where I think the starting point, and we're going to do more, okay? So I have, let me share screen. And let me get my pen in here. So the first problem I thought we should tackle is problem 19. This is from chapter 36. Problem 20 immediately next to it. Those are extremely important problems. So I really want you guys to understand how to do this kind of problems, because come test time, you'll be on your own, okay? Then problem 57 and 58. Problem 61. This is just a starter, okay? These are just to start with. So again, we're going to meet on Monday where we go through some more problems like this ones and some more problems actually from chapter 35 and chapter 35, 36, and even we can also touch base with 33 and 34 to get an idea into how the exam would look like potentially, okay? So let's start with from the first, okay? First problem, problem 19. It tells you in figure 3612C. Let me find what this 3612C looks like. Okay, 12C. 12C. Basically, calculate the central diffraction contains exactly 7 interference fringes. So let me show you what that figure is. So I'm doing this problem here. Remember the formula that we ended up with for the intensity is going to be the intensity of the central beam times cosine of phi over 2 squared, because everything, the intensity is squared, times the sine of beta over 2 divided by beta over 2. I probably did not use these symbols, but this term in here, beta, has to do with the single slit. Beta is 2 pi over lambda, which is k, times the slit opening, which is a, times sine of theta. Okay, where theta is the angle where you're trying to find the stuff, and phi is due actually to the separation between them. Phi is equal to 2 pi over lambda. Again, that is k, the wave number, times d. D is the separation between the two slits. So this is what's going on now. So this is a combination of the single slit and the double slit. This distance is a between the slit itself opening, and the separation between the slits is d. So now this is d sine theta. So the only difference between these two numbers is just the a and the d. Of course, the 2 in here will cancel the 2 in here will cancel the 2, and the 2 in here will cancel this 2. Okay, so this is the intensity basically of in the combined single and double slits. Okay, because this one we found it from the single slit, this one from the double slit, and this is not what you have when both of them are present. Okay, so if you plot this function, okay, in terms of theta, and you give a certain number for this one in here, it would be fun to actually do it. So, and I probably will prepare it for next time. Actually, we can do that. So the intensity look like this. So this is the graph that they are referring to. The central fringe, of course, will be bright, and it's going to be around theta equal to 0. When theta is equal to 0, phi is equal to 0 because sine of 0 is 0, and cosine of 0 is 1. 0 over 2. Cosine of 0 over 2 is 1. So this will become just 1. When theta goes to 0, beta also goes to 0 because of this. Beta is something times sine theta. When beta goes to 0, the numerator goes to 0, and so does the denominator. In this case, you have an indetermination of the form 0 of 0, and you use L'Hopital's rule to find that this whole thing becomes 1. So the central fringe is going to be actually here at I naught. So the maximum value that you're going to have is actually I naught. Okay, but then this function starts to vary with theta until at some point it vanishes because everything is positive in this expression. So it's going to be above the x-axis. So in this case, it's theta, by the way. Okay. So at some point, this function vanishes, but then meanwhile, this one also is changing. This one is actually canceling and giving you the double slit effect. And the double slit effect will always give you those slits basically as they are separated, because you can always find the m in here. Namely, this is coming. This is equal to basically multiples of lambda when d sine theta is equal to m lambda, where m is any integer you like. It can be 0 for the central fringe. So if I put that in here, d sine theta over lambda is m. So phi will be 2 pi times, phi over 2, because we need phi over 2 actually. Phi over 2 will be pi times m. So when you square pi m over m, it's either positive 1 or negative 1. So when you square it, it's always going to be positive. It's going to be 1 actually. So those are bright fringes due to the double slit. But this guy now is actually equal to 0 when theta itself is equal to 0. Okay, that is a condition. Or theta itself, in this case, let me try to make the case for it in here. When this number, when the whole thing, beta over 2 actually, no, I'm sorry, this is, yeah. When beta over 2 are multiples of pi. Okay, so this is m pi. And that condition would work too, because sine of beta over 2 is equal to 0. Okay, so this whole thing are multiples of pi will give you a condition divided by 2, of course. Pi over lambda times pi times a times sine theta are actually multiples of pi. Cancel the pi from both sides. And this is equal to 0, of course. These are dark fringes. So that means that a sine theta is equal to m pi, where m is anything but 0. Because if it's 0, then you have a 0 in the denominator. Yes, you have a 0 in the denominator, so that's not going to work. So in this case, a sine theta are going to be equal to m lambda, where m is any integer you like. So that will make this term 0, regardless of what happened in here. 0 squared times any number in here is going to be 0. So this is the condition for the dark fringes, because beta over 2 is a multiple of pi, and if it's a multiple of pi, its sign is 0. Period. because this guy will be just a multiple of pi. So this will be, the denominator will be just m pi, and the numerator will be sine of m pi, and the whole thing squared. The denominator is finite now, since m is not equal to 0. So the condition here is m is not equal to 0. Then, but in here, it's going to be 0 regardless. So this will cancel everything that happened there. So this is going to be dark fringe. And these are the points. So this is where a sine theta is equal to the first pi. This is where a sine theta is equal to negative pi. Okay. And then there will be another one. But then actually after that, the intensity starts to diminish. Okay. The intensity is actually not equal to 1 because the denominator is growing now. Because the next level for m equals to 2, the denominator in here starts to grow. The numerator is always between 1 and negative 1. I mean, yeah, until you square it, it becomes 1. But the denominator grows with m. Okay? The denominator grows with the angle beta. Okay? With the argument beta, because as m grows, this thing starts to grow. So the next one is actually going to be here somewhere, where a sine theta is equal to 2 pi, and the other one is actually a sine theta equal to negative 2 pi. But then the intensity drops by that factor squared, of course. Okay, so it's going to be something like this, and the next one, so it's going to, I'm sorry, so like this, it's going to be 0 here. I don't know why I had that. And then the next one is going to be even less, and so on and so forth. So the next one is going to be like this, and the third one is going to be barely here, and so on and so forth. Now, this is the envelope. This is that factor. Now, I need to find what's going on in the inside. The inside doesn't care. It's always a periodic function. So it's going to vanish only in the points that makes this condition equal to 0. Okay? So you will have several of them, and then it vanishes everywhere. Then several of them, then it's going to vanish, and so on and so forth, and in here. So this is the picture that they're referring to, basically. So the center bright fringe, so this is how the spectrum would look like if you open it. The inside will be like this, and it will have a bright fringe in here, due to the double slit, the dark fringe followed by bright fringe, followed by a dark fringe, then another bright fringe, dark fringe, and then bright fringe. So let me shade the, so these are actually bright fringes. And then there is this one is coming from the double slit, from the single slit. Then there will be another region in here of bright fringes and dark fringes, and then the dark region. Always the central fringe is wider than this one's. That is because of the single slit, and the smaller ones are because of the double slit. So this is basically, in a nutshell, the entire chapter. So the central fringe in here, this is due to the single, and this small ones in here are due to the double. Okay, that is really the whole essence of this one, because D is typically bigger than A. So the first equation that says m lambda is equal to d sine theta will give me a theta, or sine theta if you wish, as m times lambda over d. Because d is bigger than a, this number is expected to be bigger than, so these are the bright fringes, of course, from the double slit. The dark fringes, or the cancellation, Drake, sorry. Sorry about that again. So the cancellations, dark, that's what I meant to say. Dark. Okay. Are given by m lambda, and let's use different symbols in here. So I'm going to call this one m prime. Okay, m prime sine of m prime lambda is equal to a sine theta. These are cancellations now. So this will give me a condition of theta that is equal to m prime times lambda over a. Well, m prime and m are not the same. M prime is referring to this number, to this big numbers in here. You have 1, you have 2, and so on, so 3. And m is referring to this numbers. This is 0, this is 1, this is 2, this is 3. This is probably 4 in here, but it cancels. 5, 6, 7, and 8, and 9. So you can have a lot from the left one. Because D is bigger than A, though these thetas in here are smaller, because they're dividing by a bigger number than A. This distance between the slits is typically bigger than the opening of it. Otherwise, you have a problem with that. Okay? So this is, in a sense, part of the lecture, actually. So, and I'm just referring to this picture in here. So let's do problem 19 now. So problem 19 says the following. Referring to this picture, the central diffraction maximum contains exactly 7 interference fringes. And in this case, D over A is equal to 4. So what they're saying in here, there are 7 of them. So there is the central one, and that is m equals to 0, and there is m equals to 1, and there is m equals to 2, and there is m equals to 3 inside. On the opposite side, there is m equals to -1, m equals to -2, and m equals to -3, and so on and so forth, okay? This one, m equals to 4, corresponds to m prime equals to 1. In other words, the fourth one cancels because of the fact that this one is actually where the destructive interference happened because of the single slit. So let's find the condition on A now. So we know that sine of theta, and it's the same theta, by the way, because we're looking at the same points on the graph in here. So sine theta, this angle that we just are requiring, is 4 times lambda over D. And the same time must be equal to m prime, which is 1 times lambda over A. From here, cancel the lambda from both sides and move D to the other side and A to the other side. You will find that D is equal to 4A. So if D is equal to 4A, meaning this distance is 4 times bigger than the width of the single slit, then in this case, when I plug in m equals to 4 in here, I will find an angle, and here is the angle. Sine theta is equal to 4 lambda over D. That is good. But that will correspond to the same theta that makes this condition true also. And that theta corresponds to m prime equals to 1. In other words, let's find it, for example. Let's find this angle in here. Sine theta equals to, did they give us any numbers in this problem? No, they did not. So we're working on basically conceptually. So we found theta. Let's call it this one, the theta for 4. Okay, so I'm going to call it theta 4. Theta 4 is equal to 4 lambda over D, correct? That is exactly what it is. If I take the fact that D now is 4A, then it's going to be lambda over 4A. Cancel the 4 from both sides, and this is the same thing as lambda over A, or 1 times lambda over A. And that is the other condition. Okay? That is another angle. So the sine theta 4 is the same thing as the first angle where this thing cancels. So in that case, it's going to be a pure nothing. So although we're expecting to have a bright fringe from the double slit, but that is actually where this term is equal to 0 in the expression. So even though this is a maximum is equal to 1 squared, this is going to be 0. So that's it. One of them is 0, the whole thing is 0. It doesn't matter which one is that. Same thing in here. We continue for the next points in here. Okay, so that is the question here. What must be the ratio D over A be if the central maximum contains exactly 5 fringes? But now here's the question of the problem. Instead of 7, which is m equals to 3 now in this case, on both sides, so you have 1, 2, 3, and 3 on the other side, that's 6, plus the central one. You always have an odd number of the double slit, okay? So in this case, we want m equals to 3 to correspond to m prime equals to 1. That's what we want, really. So that is the condition with which we want this thing in here. So the question is, what is the ratio of D over A need to be? So that is the question that they want us to answer. Okay. So if we do that, let's do a similar analysis. So we know that the angle θ3 is the one that makes this is true. In other words, 3 times lambda over A, over D. So this is the bright, or the third. When I say the third, I mean outside of the central one. Central one is going to be always bright. The third bright fringe. Satisfy this equation. This must be the first cancellation due to the single slit. If that's the case, then I will have 0, 1, 2, and that's it, because the third I required it to cancel. So the third, what I expected the next bright, this will cancel it. Same thing on the other side. I have -1, I have -2, and the third, which is -3, also I expect this one to cancel it. So in other words, in here, I will only have 5. That's the question. They want only 5. They don't want 7, like the picture was showing you. So we want 5 only in the central fringe. So if we do that, then this must be equal to the same angle sine of θ3 must be also satisfying 1 times lambda over A. And this, of course, from the first equation is equal to 3 lambda over D. From here, cancel the lambda from both sides, and I will find a condition on how A and D are related. So I can move D to the other side. It's going to be D over A equals to 3. So that means that D over A must be 3. If D over A is 3, then in this case, the third bright fringe from the double slit will be the first cancellation from the single slit. Okay, and inside I will only see 5 bright fringes only. So the region of the middle will only see 5 of them, not 7 like the first case. So that is a condition for finding basically this fact that I will only have 5 of them. Does the problem make sense, at least so far? Because we still have more problems. Hopefully they will make it clearer, okay, down the road. Here is the second question. The second question, part B in here, how many fringes are contained within? Okay, there is a mistake in the book because I tried to think of this question very hard, trying to see how it's going to be. And I think there is a mistake because here is the question. How many fringes are contained within the first diffraction maximum? Well, there are 5. You just told me. If this is the question, this is an easy question. But I think what they meant with it is the second. Because here's a problem, as I was saying in the beginning. This must be bigger than the next one. And the next, all of the others, they will be roughly the same size as this one. So this one in here, if it has 5, this should have less than 5. It could have 4, it could have 3, it could have 2, it could have 1, or it could have none. If this whole thing is basically the entire thing. Okay, but it cannot have more than 5. It cannot even have 5. Because this is less. So the question usually is the second one. Because this is the second one. We went from m prime equals to 1 down to m prime equals to 2. We want this region. How many am I going to have in there? Does this make sense? So now we need to find a number less than 5. So that is the question. So let's find m prime now. And find the angle with which cancellations, the next cancellation happen. Next cancellation will be for m prime equals to 2. Because we just found the first one. And that will be some angle in here, which I'm going to call it sine of theta prime equals to 2. Theta prime 2 that must be equal to 2 times lambda over A, okay? And 2 lambda over A from this equation, this is the condition to have 5 bright fringes inside the first one, the first cancellation. So I'm going to have D, which is 3 over A, which is going to give me in here, in this case, A equals to D over 3, correct? If I solve this equation for A, because I need to plug it in here to see how it's going to work for the other one. So it's going to be 2 times lambda over D over 3. And that is, of course, 6 lambda over D. Now, if I look at this expression, I know that is the 6th value in here. So that means that 6 sine of theta 6 is the one that corresponds to this same angle. So M must be equal to 6. So here is the deal. We saw the central bright fringe has 5. There is 1, 2, 3, 4, 5. This is the central one, I'm sorry. So there is 1, 2, and there is -1, -2, correct? This one is canceled, and it's canceled because of the single slit. Now the next one, so this is 4. This is actually 3, okay? Then 4, 5, and the next one that cancels is 6 actually. M equals to 6, and it's canceled because this is M prime equals to 2, and this is M prime equals to 1. So how many bright fringes I'm going to have in this one? I'm going to have only 2 of them. The central one has 5 of them. On the opposite side, of course, there is a cancellation in here, and there is this one too, and there is another cancellation. This one will have 2 in it too. Does this make sense to you why the central one is so wide now? Because it has more of this than the next one. Come on, guys. Yes, no, maybe. It's okay. If it's maybe, it's okay, because this is the first time you probably gotten into this point in here. Did I start the recording on this class or not? Oh, yeah, there's one. Come on, guys. Okay, very good. Yeah, okay, very good. I'm glad to hear that. So listen, it will not really make perfect sense to you guys until you actually hammer these examples time and time again and you start to think about it. You have 2 equations really that you want to satisfy. And the integers are not necessarily the same though, okay? The first one is bright. And that is d sine theta equals to m lambda. And the second one is cancellation or dark, no matter what. And that is a sine theta, where the theta have to be the same if I'm looking at the same points in here. Because if this is the central fringe and I'm looking at this point, is it dark or is it bright? Then in this case, this is theta. It's the same theta for both of them. Okay, doesn't matter which one I'm talking about. Is equal to another integer, not necessarily the same thing, of lambda. Because a typically is less than d, this integers move slower compared to this one. So that's the only difference between these two. So this is problem 19. So let's do problem 20, which hopefully will reinforce this problem for you guys. Okay. And it's actually, in terms of the level of difficulty, this is twice as difficult because of the fact that so there is a typo on problem 19. I believe it is, because it doesn't make sense that they gave you 5 on the central bright fringe and central maximum for the single slit, and then they ask you how many they are. You just told me put 5 in there. So it's the second one. It makes perfect sense, because then you find that there are 2 of them only in the second one, because m equals to 6 corresponds to m prime equals to 2, and that is where this second term cancels. This term is equal to 0, okay? Because the numerator is equal to 0. So in this case, doesn't matter what's happening in it. Yeah, it's a maximum in here. So what? You're multiplying it by 0. It's going to be 0. Okay. So that is basically in a nutshell what's going on with this whole thing. So let's do problem 20 now. Problem 20 says the following. Consider the interference pattern produced by two parallel slits of width A and separation D. Again, we're going back into the same situation as before, and they gave you D equal to 3A. So here's the deal. So we have A is the single slit separation, and D is the separation between the two slits, and they tell you that D is 3A. So we are in this picture. We are actually looking at this kind of spectrum, okay? There is a big one in the middle, there's a bunch of them together, and then there is cancellation, and there is a couple of them on one side and a couple of them on the other. I didn't calculate this one, but you guys can calculate it too. It's not hard. So we find, for example, so let's do it for just for the fun of it, okay? Let's do the third one, not the next cancellation, not the second, the first cancellation we already found it. The second one is here. The third one corresponds to m prime equals to 3. M prime is equal to 3. That means that A sine theta is equal to, or sine theta, let me calculate sine theta, I don't need A. So sine theta, which I'm gonna call it 3 now, prime, must be equal to 3 times lambda over, be careful with the 3 now, because you might not find it, okay, because it might be outside of this condition might be greater than 1, in other words, which makes this angle an imaginary angle which doesn't exist. Divided by A, this must be equal to 3 times lambda divided by A, and A is D over 3. So this is going to be D over 3. So this is 9 times lambda. So that corresponds to M equals to 9. M equals to 9. That means that 7 and 8 are also bright. This is 7, this is 8, and then 9. 9 is also, this is M equals to 9, corresponds to M prime equals to 3. So there is actually 2 slits also in here, 2 bright spots in here too. That's why typically the next bright fringes, they are always coming from the single slit, okay? They're always the same size, and they're about half this width, okay? It's actually 2.5 times bigger, okay? And so on and so forth. So you can do any number you like, as long as this number is still real. Because I'm doing it symbolically, and maybe if I plug in the values in here, lambda over D. If I plug in these numbers in here, I will find an imaginary number in there. I mean, this number becomes more than 1, and there is no angle that makes this thing more than 1. Okay, that makes sine theta prime. So there is a limit basically on what these things can go. So the slits are illuminated by normally incident light of wavelength lambda. So all of the setup so far is everything is standard, no values in there. First, we ignore diffraction effects due to the slit width. So basically we ignore A, okay? At what angles theta from the central maximum will the next 4 maxima and then the slit interference pattern occur? Well, at what angle? So we have theta 1 corresponds to sine of theta 1 equals to 1 times lambda over D. Theta 2 corresponds to sine of theta 2 equals to 2 times lambda over D. And you got it now, because those are the maximum. I have 2 of them, by the way, okay? This is positive and negative, okay? So we have 1 on top and 1 on the bottom, but we are only on one side. So we're looking at only the next one. So theta 3, obviously we have theta equals to 0, okay? But theta equal to 0, that's not, they don't count one, they just want the next 4. So theta is equal to 0, that is true, that corresponds to M equals to 0, because we're looking at the effects of the double slit, and there it's a bright spot there too. So theta equals to sine theta 3. Obviously, this is an equation that you can, the problem that I see in my exams for my students in here, the problem I see with my exams for my students in here and this is a common problem that I really hated when I see it, is my students forget to make sure that they are working, I mean, they're probably working in radians, and they forget to convert things to the proper degrees or do it the other way around. So when they plug in for the next equation, they have something which is clearly in radians and they plug it in degrees and then messes up things for them. So make sure the mode of the calculator, you're aware of it. Calculator mode. So if you're doing calculator, is it degrees or is it radians? Okay, make sure you solve this issue first, because you're going to find an arc sine of everything in there. You're going to be working with a lot, especially if the ratio is not really an even number. So let's say, for example, one is 4 and the other one is 3 millimeters. Now we have a big problem. This ratio is not exactly 1. So there will be a lighter version of a fringe from one of them. Okay, so this is lambda over d. And the last one they want us is sine of theta 4 is equal to 4 lambda over d. So these are the first 4, okay? So first, we ignore the diffraction effects to the slit at what angles theta from the central maximum will the next 4 maxima in this 2 slit interference pattern occur. Your answer will be in terms of d over lambda. So this is of lambda over d, we found it, okay? Yeah, it's the same thing, d over lambda. Now, we include the effects of the diffraction. If the intensity at theta equal to 0 is, theta equal to 0 degrees is I naught. What is the intensity at each of these parts in A? So here is the problem now. We know I naught is the intensity for theta equals to 0 degrees, actually. That is true. So I is equal to I naught. Let's find it for I1, which corresponds to theta 1 now. So that is going to be I naught cosine of phi 1 over 2 squared, the whole thing squared, I'm sorry, not this one only, times the sine of beta over 2 over beta over 2 squared, okay? And we need to find what that angle is. Remember, phi 1 over 2 is equal to, what did I write it? Is pi d over lambda times sine theta. So phi 1 over 2, I need the whole thing, okay? It's pi d over lambda times sine of theta 1. Well, I just found what sine of theta 1 is. Sine of theta 1, if you can clearly see, it's lambda over d. So this becomes pi times d over lambda times lambda over d, because this number is actually sine theta 1. So cancel the d from both sides and the lambda from both sides, and this angle is just pi. So I'll have a cosine of pi, that is phi 1 over 2, not phi 1. Cosine of pi squared. Cosine of pi becomes -1. When I square it, it becomes 1. That's easy, okay? So there is no problem in here. It's here that we need to find things, okay? First of all, beta over 2. We need beta over 2. We don't need beta, which is pi a over lambda times sine of theta 1 now. It's the same. We need it for beta 1, by the way, because we need to replace beta for theta 1, basically. So beta 1 then is going to be pi a over lambda times lambda over d, where lambda cancels the lambda, and a over d, because they tell us a over d, we need a over d actually, is equal to 1 over 3 from this expression, okay? So that is actually, cancel this with this, and I will be left with a 3 in the denominator. So this answer is pi over 3. So beta 1 over 2 is pi over 3, or 60 degrees. Here is a problem. If you do the calculation and you plug in this is exactly my point that I want you to really pay attention to. It really makes or breaks a lot of the questions that you have in the exam. This is not 60 degrees, not 60 degrees here. When you plug it in here, You plug in pi over 3. You don't plug in 60 degrees. So if you're calculating and you have an arc sine somewhere and you plug the value and you find something in here, you might be tempted to think that, hey, this is just 60 degrees. Pi over 3 is 60 degrees. So I plug 60 in here. That is wrong. Pi over 3 is about 1. This is about 1. Pi is 3.14 divided by 3 is slightly over 1. It's 1.3? 1.03? So it's about 1. And that could create a big difference, because then you're going to square that 1 versus you square the 60, which is going to be 3600. Yes, they cancel in here because of the fact that D is 3A. But the first one they cancel perfectly because phi 1. Phi 1 over 2 has actually pi d over lambda. This one has pi a over lambda. So here the ratio is 1 and here the ratio is 3. Make sense, Justin? Very good. Listen, the biggest deal I'm trying to emphasize in here, and I cannot really emphasize how important this is, because your answer could be big deal different than the correct one. Because when you divide by 60 squared, it's divided by 3600, so this intensity will be practically 0. Whereas when you divide by 1 and you square it, it's actually a meaningful answer. So let's do it. Okay. So I1 will be I naught times -1 squared, so that's easy, times sine of this angle, sine of pi over 3 divided by pi over 3, the whole thing squared. Here, you can put 60 degrees if you like and work with degrees. Here, you cannot. It's a no-no. In the denominator, you work with radians in the denominator. So let me see if my calculator is available. And let me make sure that you follow my calculation so that if I make a mistake, you catch it, and hopefully you do the same thing while you're taking an exam. So let me stop sharing that side and let me share the calculator. Okay. So what I have in here, the expression, first of all, -1 squared, I'm not worried about it. I'm worried about the sign. Here is the thing. My calculator right now is in degrees. So if I change it to radians, I'm in good shape. I can work with the denominator. Denominator has to be pi over 3 no matter what. The numerator, the sign, I can put pi over 3 now with confidence. So what I need is actually sine of, open parentheses. Okay, I need to square the whole thing right away. I don't want to do this in baby steps. So sine of pi over 3, close the parentheses. Now I have the sine, I need to move a little out of it, divided by, open parentheses, pi over 3, close the parentheses, close the big parentheses, and now square the whole thing. Okay, so this is what we have in here. So let's see what that gives me. It gives me, this is the whole deal. This is not anything in it. 0.68 or 68% of I naught, basically. I naught times 0.68. Okay, I don't know how many sig figs in this problem. They don't have any sig figs. Okay, they don't have any sig figs. So I'm going to retain 4 of them. I mean 3 of them. So it's going to be 0.684. So let me stop sharing and let me share with you the other one. Share the notes, and let me move this things back to where they were. This one also out of the way. So this is saying to me equals to, no, I don't mean to do this. Where is my pen? Here. This is telling me now it's equal to 0.684 I naught. In other words, when I moved from, it's the same problem in here. This angle in the graph, what is the graph that I was drawing? This one is I naught. The next one is 68.4% of I naught. Okay? That is basically what this is saying. Now the third one, theta equals to, I'm sorry. So this is beta 1. Let's define the 2, I2. The next intensity, which is going to be I2. I2 will be I naught times cosine of phi 2 over 2 squared times the sine of beta 2 over 2. The whole thing is beta 2 over 2. The whole thing is squared. Same thing. Well, I know now that phi 2 over 2, I need the whole thing. It's pi over d over lambda times 2 times sine, times sine of theta 2. We already figured it out. It's theta 2, okay? Times sine of theta 2. Sine of theta 2, if you guys remember, it's 2 times lambda over d. So that's the only difference in here. So this is going to be pi d over lambda times 2 lambda over d. Cancel the d and cancel the d and cancel the lambda and cancel lambda. And this number is 2 pi. In other words, this is going to be a cosine of 2 pi. And the cosine of 2 pi is positive 1. When you square it, it's going to be 1. So we don't worry about this one, honestly, because of the fact that this is how we get these numbers anyway. So we're going to always get 1, either positive 1 squared or a negative 1 squared, which is going to be 1. This is the problem. This is what makes the intensity go down. It's the single slit that is affecting it. So beta 2 now over lambda, beta 2 over 2 is going to be pi a over lambda times the sine of theta 2, and that is pi a over lambda times 2 lambda over d. Again, lambda cancels the cancel, and d is 3a. So this becomes 3, and everything will become 2 pi over 3, and that is 120 degrees. So again, I'm going to plug in here sine of 120 degrees or sine of 3 pi. So since I changed my calculator to so let me show you with this calculator how I do it, okay? Because it's kind of easy. So let me share with you the screen. Oops. Where is the share button? I don't know if your calculator can do that or not. So all I do now is copy this formula and change this number in here, because I know it's going to be 2 in here, and I know in here it's going to be times 2. I can put it in front just to make this thing. And this calculator recognizes if you put a space, it's going to multiply things for you. So all I have to do now is enter, and it's 0.171. So it dropped to 17% now. So this intensity dropped to 17% now. So I2 so that's the whole thing squared. So I2 is equal to 0.171 I naught, or I use the same formula, by the way. Now I plugged in all of the numbers. I probably did not write the formula, but hopefully you guys can see it, that this is about 17.1% of the original I naught. So in other words, this is the point I'm looking at in here in the graph. It's this point. This is about 17% now of I naught. This is I naught itself, okay? So now I hope that you guys see the whole thing. Now I can do m equals to 3 with ease. So m equals to 3. Well, m equals to 3, or theta 3, I should say. I3, we call them I3. I3 is going to be I naught times cosine of phi over 2. I could stop from this point on working on this angle in here, because then it's going to be 1 no matter what. The whole thing is going to be 1 times the sine of beta over 2, and that is beta 3. The whole thing divided by, of course, beta over 3, beta 3 over 2. The whole thing is squared. So now let me find phi 3, just to reiterate this point in here. Phi 3 over 2, not phi 3, is equal to pi d over lambda times sine of theta 3 and that is equal to pi d over lambda times 3 times lambda over d, cancel the d, lambda and the d, and I will left with 3 pi. Cosine of 3 pi is -1. 1 is squared, it is going to be 1. That's the point. As long as you're working on the bright fringes in here for the double slit, this is true. But if you're working on any other points, it may be different too. So this could be a different value. Okay. Now here is the thing that that's going to make a difference. So I have pi 3 over 2 is equal to, again, pi a over lambda times sine of theta 3, and that is equal to pi a over lambda times 3 times lambda over d. Okay, again, we can go and check these numbers in there from the top, and you see that this is correct. Lambda cancels lambda, and d over a is 3 in here, and 3 cancels the 3, and I'm left with pi. I don't need the calculator for this one because I know sine of pi is equal to 0. So I3 is actually equal to 0, regardless of what the denominator is, regardless of everything else. So I3 is equal to 0. And that is exactly the argument that we were talking about, that this point in here is actually canceled because of the double slit, because of the single slit, I'm sorry. This is a dark point. This has no intensity. I3 is 0 there. Since we calculated the M4, let's do it for 4. And it should be, as I said before, less than this one in here, less than 17%. So we found 1, 2, and 3. And then now we're going to, and we found 0, and the other one should be more than 0. So let's do theta 4 now, just to close this thing in here and answer all the questions for this problem. So now I4, which is equal to I naught times cosine of phi 4 over 2 squared times sine of beta 4 over 2 divided by beta 4 over 2 squared. Okay, now phi 4 over 2 is going to be pi d over lambda times sine of theta 4. And that is pi d over lambda times 4 times lambda over d. Cancel the d and the lambda, and I have 4 pi. Cosine of 4 pi is positive 1. When I square it, it's going to be 1 squared. I mean, it's going to be 1. So we're fine. This is true. Now here is the problem. I need to find beta 4 over 4. And beta 4 over 4 is equal to pi a over lambda times sine of theta 4. And that is equal to pi a over lambda times 4 times lambda over d. Lambda cancels the lambda, but this is actually 3 because d is 3 times, and this doesn't cancel now, it's 4 pi over 3. So now I have to do the calculation again, similar to before. So it's going to be I4 equals to I naught times 1 squared, negative 1 squared if you like, times sine of 4 pi over 3 divided by 4 pi over 3, the whole thing squared. This better be less than the other. So I'm going to switch one final time to my calculator screen. Okay. So it's going to be here. So in other words, I'm just trying to take advantage of the fact that I did that before. So change this number to 4 now, and change this number to 4 now. And let's hope that this one is less than 17%. And it is. It's actually 4.27%. It's 4% basically, slightly more than 4%. Exactly how this thing is working. So let me stop sharing. Let me share this slide in here. So the answer is 0.0427 I naught. So in other words, this intensity I4 is 4.27%. We went from 100% in the central one, and we're down to 4% by the fourth time, by the fourth one. So this intensity in here, it's a lot dimmer than the other. So this is m equals to 4 now. I mean, we went a step beyond. So this was 100%, and we found a 68%, which is almost 70%. Then we dropped to 17%, then nothing, 0, and then we went up to 4%. This should be less than the other two, and so on and so forth. Obviously, this starts to dim more and more and more as we go along with this problem. I know we spent a couple of hours on this two problems, but remember, I spent at least 15 minutes introducing the whole thing. I mean, going through the entire class from beginning, from first time when we met until today. And then I also talked about the chapter and a little bit, I mean, some of these concepts related to these two problems. So, is this the last question? Which double slit interference maxima are missing in the pattern? Well, 3 is. So that's a question 3. Compare your results to those illustrated in figure 36.12c. In what ways are your results different? Okay, basically we did the comparison and we were going along. So they want you to compare to this graph basically, okay? So they're matching, the other one had actually an extra 1 here, we did not, because the other one had actually 7 inside. Okay, had 1, 2, 3, the central, plus 1, 2, 3. So it had 7 in here, we actually had 5, that's all. Because the whole thing changed from m equals to 4 to m equals to 3. So that is basically what the only difference is. But the graphs are similar in the sense that the intensity starts to go down and more as we move along. Okay, so we did problems 19 and 20. We still have more problems to talk about. And I know I did them in extensive detail. And we went through all of the details that you would want to go through. And I hope that you guys have them clear. And if it's not, please let me know so that we can work out these details. And if in case you need help with something else, please let me know also so that we can work it out, because this is the entire course that you guys have. We still have more problems from this chapter. So we're meeting on Monday. And that's it. Any questions? We may do the following, okay? And it's up to you guys, okay? I'm hoping, let me see, since we're done with the labs, maybe we should not meet in the morning and meet in the afternoon so that we don't have the constraints of time, so that if we feel like, okay, after an hour we're good, then we stop. If after 2 hours we're still good, then, and we don't want to stop, we can continue. And if we have up to 3 hours and something. Does this sound like a better deal? What do you guys think? Of course, I will send it to the other people who are not here who might want to choose to attend. Okay, at least one person is good. The other one sounds good. Okay, so this is what I'm going to do then. I'm going to send basically to everybody, because basically all we're doing now is applications. Very good. So everybody agrees on this, at least in here. So I'm going to send for the people who are not here saying that, okay, we're done with the lecture. We're doing only problems now, so that we don't fall under the constraints of the 1 hour and whatever, 25 minutes. We're going to have our lab, the afternoon lab on Monday, dedicated to this one, so that you guys are free in the morning because there is no lecture or nothing else. And if after an hour and a half or 2 hours you guys feel tired, please let me know so that we don't want to continue this one. And we still have other classes too that we can catch up with, questions and things like that. Okay, let me stop recording. Where is the recording button in here? Stop.